Ladies and gentlemen, welcome once again to the Simpkins Physics Corner. It's your host, Mr. Simpkins, with a little bit of projectiles recap. This week we're going to launch into angled projectiles, and so I want to give a quick recap of the skills now that it's been Christmas break. You may have forgot a few things. So here's all the equations we use, and if it's been a while since you looked at physics, you might be like, I forget what all this stuff means. So let's do a quick reminder. Fill this out in your notes as we go. XF would be final horizontal position. XI would be initial horizontal position. So X means horizontal position. Y means vertical position. So Y, how high? If you think of the y-axis in math class, it's where are you on that y-axis. T, of course, is time in seconds. VI means initial velocity, so like here in this equation. A, which we see in this one, is acceleration, or G over here, which G has a specific value, negative 9.8 meters per second squared, but both of those are meters per second squared. Both of those are acceleration. Vx is your x component of velocity. For example, if you shoot up in the air, this is your Vx. And then the upward part of your motion is the Vy. So the x is your horizontal velocity, and the y is your vertical velocity. And so that's a quick little recap. If you need to pause the video right now, you can do that and fill that table in on your notes so you have this as a reminder. So I'm going to walk you through 3 examples today to get our minds re-engaged, to get refamiliarized with the equations that will prepare us for our shooting lab that when you come back in next time. So here it goes. First type of question, keep it nice and simple. A kid jumps on a trampoline. If the kid rises to a height of 1.5 meters above the trampoline, how long did it take him to reach that height? So we got a trampoline here. Boom, there it is. There's the kid. So we'll call this y equals 0, right? And then the kid goes, woohoo, and jumps up here. So there's our kiddo. And it looks like that kid went to a final height of 1.5 meters. So the first question says, how long did it take him to reach that height? So we're solving for time. Well, we notice that this is straight up and down, and we know that if we throw something up, what goes up must come back down. So what we can say then is the time it takes to go up and come to rest is the same amount of time as it would take if I were to drop that kid from rest and get back down to the trampoline. So we're looking at our free fall equation. Let's look on down there in the slides. For straight up and down only, I put a little note there for you guys. But when it says how long did it take him to reach that height, we're going to do t equals the square root of 2y over g, because that's the time it would take to fall if you drop something from rest, which would be equal to the time it takes to travel from the bottom up to the top. So we're going to fill this in here. We got 2 times 1.5 meters over 9.8 meters per second squared. And we take the square root of that, and we're going to get our time. Now, don't be a bully. The poor little square root symbol, all it wants to do, guys, is participate in math and science. And so many of you, you'll write this equation, and then you'll just not take the square root. How terrible would you feel if all you wanted to do was participate in math and science, and you were bullied out of existence, and no one ever acknowledged your square root symbol? That would be so sad. Don't be mean to the square root symbol. Be sure to take it. And so that is the time of 0.553 seconds. Now when I ask how fast was the kid moving when they left the ground, how fast is velocity or speed? And this equation technically is for when you drop something, how fast is it going when it hits the ground, is v equals gt. But as we know the symmetry of projectiles, if you toss something up into the air, the speed it leaves the ground is going to be equal to the speed that it returns to the ground with. And so when we say how fast was the kid moving when they left the ground, all we got to do now is v equals gt. So let's go ahead and drop that in. We got 9.8 meters per second squared times a time of 0.553 seconds. And we'll multiply those, get a little 9.8 action. It looks like 5.42 meters per second, because it says how fast, and we solve for velocity, would be the speed when they left the ground. So what I want you guys to do right now is try this one out all by yourself. Math magic. The first part is 2.02 seconds, doing the same thing we did for our first example, using that time equation from the free fall. Just like number 1 for part B, we are going to do v equals gt for 19.796 meters per second. So now that you've had a chance to try those on your own, I just want to get you familiarized again with what equation to pick, the mechanics of how to use it. Let's go to a different kind of example. See, we started to talk about components of velocity. We played the gorillas game where the little gorilla guy, where the little gorilla guy was over here, and we had bananas, and there he is, and he goes, and he throws the banana at the other gorilla. We were looking at velocity and angle and how that impacts the flight of a projectile. So let's look at this one. A stuntman is launched from a cannon with a speed of 15 meters per second at an angle of 25 degrees above the horizontal. When we say that, we just mean horizontal is like the horizon, right? It's the x-axis. So you're kicked 25 degrees up from there. Question says, what are the components of the stuntman's velocity as he leaves the cannon? Well, if you look at your equation sheet, projectiles, vector components, the equations are right there for you. So Vx equals and Vy equals. Now I'm going to pull up my virtual TI calculator, which you guys could use at home as well. To remind you, the very important mode you have to be in. Some of you turned in an assignment last week and all your answers were wrong, and it was tragic. And it's not because you did anything wrong, except for this one step. You got to click mode, go down to the right one, and choose degree mode. All right, if you're in degree mode, now you're going to get the right answers. So let's see what our answers are. So for the Vx, if we look at our equations down there, oh, it cut off my equations. Oh no, there it is. Vx it says is V cosine theta, and Vy it says is V sine theta. When I say it says, I mean the equation right down here, which also found on your equation sheet. And V is for the velocity, so that's 15 meters per second. Cosine of 25 degrees. And then this one is 15 meters per second. Sine of 25 degrees. So if you plug those into your calculator, that's in degree mode. Okay, make sure it's in degree mode first before you do that. Go rewind the video if you have to and check out how I just did that. The cosine, or the x component, is going to be 14.86 meters per second. That's pretty big. And oh, you know what? Guess what mode I'm in, guys? Radian mode. I did it on the computer, but not on my actual calculator. So that answer would be wrong. And let's try that again. 15 cosine of 25. The actual answer here is 13.6 meters per second. So that's what you get if you plug it into a calculator that's actually in the correct mode, which is degree mode. Then we do 15 sine of 25. That's going to be 6.34 meters per second. Now, I want to note something to you guys here. You notice this arrow here representing our vector, or our velocity, is pretty significantly moving to the right, but not moving up and down too much. Check out the components. You see how it is significantly moving to the right? Horizontal, Vx, 13.6. It means this part is 13.6. It means it's moving 13.6 meters per second to the right as it is launched. And it's only moving 6.34 meters per second up as it's launched. And so based on your drawing, and if you draw with the correct angle, you can figure this out ahead of time a little bit. So that's a sample. What I want you guys to do is pause the video and try this one out for yourself. And magical math happens, and if you plug it in correctly, you will get an x component here of 3.06, a y component of 2.57 meters per second. Again, what does that mean? Well, at 40 degrees, let me draw this one more time for you. Draw this for you here. At 40 degrees, like this, all right, if you launch at 4 meters per second as the overall velocity, the pieces of your velocity, the Vx piece, the horizontal piece of your velocity, you're going to be moving 3.06 meters per second horizontally. See how that's a shorter side of our right triangle. And you're going to be moving, it's kind of a crappy drawing, sorry about that, but you're going to be moving 2.57 meters per second vertically when you leave the launch. So shooting your suction cup arrow just like that. Now, things are going to get a little crazy here, all right? This is technically not a new equation, but I'm going to show you a calculator trick to save you lots of work. Do you want to do more work or less work? I think more efficient work sounds good to me, so I'm going to show you how to do that on your calculator. But let's look at this, because this is going to be the pre-lab, or the lead-in to what you need to know how to do when you do your lab challenge next time I see you. All right, so lab cannon launches a ball at a speed of 3 meters per second in a direction 45 degrees above the horizontal. So I'm going to draw this over here, because I always draw my physics problems. Helps me get some context to what's happening here, and helps me organize everything. So there we go. The cannon sits on top of a table. Oh dear, here we go. That is 0.9 meters high. Using an XYT table, organize the known values, find the components and fins, and find out how far away the ball lands from the table. Now, when we say how far away from the table, we mean this, and that's horizontal distance x. So the big goal of this problem is to solve for x. How far away does it land? Now, when we say XYT table, remember that's just a little organization tool that we use to break down all the pieces of a puzzle that we know here. You'll notice that 3 is neither all horizontal nor all vertical. In fact, it's part of both, right? And so we need to do the components just like we did in the last problem, Vx and Vy. I use the same equations. So you'd use 3 cosine of 45. And I'm going to write all the details here because you guys can use this as a reference when you're doing your lab challenge. So 3 cosine of 45, that's going to get me 2.12 meters per second. And for the Vy, that's going to be 3 sine of 45, which guess what is the same number. So that's going to be 3 sine of 45. Because of that special 45-degree angle, it turns out that Vy and Vx are equal. All right, it's because of the 45-45-90 rule that you might learn in geometry. Okay, what else do we know? We know the height. Okay, so this means that it started, y initial was a height of 0.9 meters. And if it goes When it comes back down, the y final is 0 because it's on the ground. It has a height of 0. Okay, so that's why the y initial and y final work out the way they do there. We also happen to know that g is negative 9.8 meters per second squared. Anything that is in free fall or a projectile flying through the air is going to accelerate downward with an acceleration of 9.8 meters per second squared. But what we need to put together here to use this equation, and we're going to use this equation, if you remember the x, y, t table, the first thing you solve for, t is key, and you want to solve for time first. So that's what we're going to do. But if you look at your equation sheet, you won't see an equation just like t equals, because this is a hard problem. And so what we're actually going to have to do is dig t out of this equation right here. So let's go ahead and plug this in. We got yf equals, all right, here we go, 1/2 gt squared plus v initial t plus y initial. So let's go over to our table of values. We wrote down that yf is equal to 0. We have 1/2 of negative 9.8. T is unknown, so I'm just going to leave it as t squared. Vi, now here, check this out. Initial velocity. We are in the y direction. So this right here, this Vy, is your initial velocity. Initially, when you leave the launch pad here, you are traveling at 2.12 meters per second in the vertical direction. T is also unknown, so I'm going to leave it there. And plus 0.9 meters. So look at your list of knowns in the x, y, t table and look at the equation. You can see how I got there. Now, grab your calculator because it's time to make this calculator do some work for us. All right, check this calculator swag out. If you, here, where's mine at? Here we go. If you use your calculator, this is what's called a quadratic equation, okay? It has a t squared, a t, and a nothing t at the end. That's a terrible way to put that, but I'm a little short for time here, so let's rock and roll. Here's how you make your calculator solve this for you. You hit the y equals button. So if you look down here in my directions, it says hit the y equals button, all right, and type in your function. So here's our function. Now, you'll notice 1/2 of negative 9.8, that's negative 4.9, okay, so I'm going to type that in. And this t squared, I need to give my calculator the variable. So check this out. This button right here, click on that. It'll show up as x, but it's our unknown x. It's our time that we're solving for. And then down here is the x squared button. So look at this function we have written down and look at what I just typed in my calculator. Do you see how they match? Negative 4.9 x squared. Then you're going to do plus 2.12x. Okay, that's what I just typed in right here, 2.12t or 2.12x. And then finally, plus 0.9. Okay, so now I've entered the function in my calculator. If you look at the slide here, the next step is to say graph. It's going to make a graph of your quadratic function. There it is. Then it says choose the 0 function. Okay, sorry, I skipped a step. It says then second trace. Okay, it says choose the 0 function, so you're going to go down and hit enter. And now it's going to ask you for some information. Let me see what my time is left here on my screencast-o-matic so I don't run out of time. Oh dear, it's not going well. Oh good, I got plenty of time. This is a perfect time. It says left bound, right? So click to the left a little bit, and you see this little cursor is going to be moving for us. Oh dear. Hold on. Let me go back here. Okay, you guys hit second trace. You're here. You hit 0. Good. All right, so you need to give it a left boundary, right? So see how this little blinky guy is to the left of right here where it intersects the axis? Hit enter. Then go to the right, and you want to move far enough over. See how this now blinky guy is to the right of where it intersects the x-axis? Hit enter. And then it's going to say guess. Just go one to the left and hit guess. Now check this out. It just solved the answer for us. It told us that here at the x-intercept, the 0 is the x value here is 0.696. So what just happened? The calculator just solved for t. The calculator just solved for time, and it says that time is 0.696. Okay, so this is how you can use your calculator and the function button to make it solve for time when you run into this tricky equation. The last part is actually really easy now because we know that distance is equal to velocity times time, and our x velocity was 2.12 meters per second. Our time, we just did the hard part to find the time, but now that we got it, nice and easy here, and we plug that into our calculator to get our final answer. Of course, I want to keep my annotations. We want to plug that into our calculator to get our final answer here. So let's see what that turns out to be. 2.12 times 0.696. That is going to be a distance. It's going to land 1.47 meters away. So bookmark this video because you're going to need it for our lab challenge. This is what I'm going to have you guys do. I'm going to give you a cannon with a set angle and speed, and you're going to have to calculate where do I need to place a bucket on the ground in order to land the ball in that bucket. Till next time when I see you for lab, this is Mr. Simpkins in the Simpkins Physics Corner.